Today we are going to explain the topic of moments. What is a moment? For example, this beam, if I put on the support and I put some weight on this side, the beam will turn. Why will turn? Because this turning effect called moment, this weight made a moment which made the beam turn. If I put the weight on this side, then the beam will turn clockwise. So the moment is clockwise. If I put the weight on this side, then the beam will turn anti-clockwise. The turning effect, of course, will change according to the value of the moment. Here, the turning effect is small. Why? Because the moment is small. Why? What is moment? How do you calculate moment? Moment is the product of the force times a perpendicular distance. The force is the weight. The perpendicular distance is that distance. So the weight multiplied by that distance is the moment. Here, the moment is anti-clockwise and small. When I bring the weight here, the moment will be anti-clockwise but large. Why? Because this distance is larger. How do you calculate moment? We multiply the product of this weight times that distance. Why? Because it is a perpendicular distance from the point of turning, we call it the pivot, to the force. The force is vertical, so the perpendicular distance is horizontal. So if we multiply the weight times this horizontal distance, we get the value of the moment. What's the units of moment? Is going to be Newton meter. The weight in newtons and the distance is, we convert it from centimeter to meter. If the weight on this side, then the moment is clockwise. And how much is the moment? Is the weight times the perpendicular distance. Now, if, for example, we try to make this experiment, which is to balance two weights using this meter rule, I can put a weight, right, a heavy weight on this side and a lighter weight on this side, and they could balance each other. When will they balance each other? If their turning effect is equal. You see here, the beam was balanced. Why? Because the two moments were equal. When will the beam balance? The beam will balance when the clockwise moment of one weight equal the anti-clockwise moment of the other weight. This beam now will balance. Why it is balanced? Because the two moments are equal. The clockwise moment equal the anti-clockwise moment. Now the beam is imbalanced. Why? The clockwise moment of this weight equal the anti-clockwise moment of that weight. And we can check it. I can multiply that weight times this distance. I'll find the same answer, this weight times this distance. The larger weight for smaller distance, the smaller weight in a larger distance. We took this experiment in physics. Therefore, now we understand two things. How do we calculate moment? Moment is the force times the perpendicular distance. Moment is the force times the perpendicular distance. Right. This weight is 100 grams, right? Means its weight is 1 Newton, because 100 over 1,000, right, times the gravity, say 9.8, almost 10. Therefore, this weight is about 1 Newton. 1 Newton, and is placed in 31, 32, right, between 30 and 35, yani say at a distance of about, this distance is 32.5, 0.325, means there is a moment of 0.325 clockwise. This weight is 50. 50 means 0.5, right? Its distance from here to there is 10, yes, the more than 10 is about 11. We said we have a moment this side is 0.325, and this moment we got the weight is 0.05. That distance, sorry, by the way, this weight is 1 Newton at the distance is from 25, a distance from 32.5 to 25 is 7.5. Therefore 7.5 we divided by 100 is 0.075. Right, 0.075 times 1, 0.075 Newton meter. And that distance here is, right, this is 0.03, right, we said 7.5, 0.0725, and that is 50, right, 0.05 times a distance of 415, about, right, 11, 12 centimeter, approximately. You will get, this is about 12.5, right, 0.0625, 0.0625 times 0.5, we get 0.03. Almost the two moments are equal. Now, any reason for it not exactly equal is because there's some friction at the support here. Anyway, this proves for you one thing, that the clockwise moments equal the anti-clockwise moments. And this is when we have the beam balanced. When is the beam balanced? When the clockwise moment equals the anti-clockwise moment. Now we should know one more thing. There's also a balance of forces. Means the total force up here is equal to the total weights down, which is these two weights plus the weight of the ruler. Therefore we have balance of forces and we have balance of moments. In AS Maths, most of the problems will not be one support? No. It will be a beam on two supports like this. Most of the problems we are going to solve will be like this. A beam in two supports. Here we will have no problem in making the beam balanced because the beam already in two supports. If I say now, if the diagram is symmetric, what means symmetric? This distance is same as that distance. Then, right, and we know that the weight of the beam in the middle, so the weight of the beam is equally shared by the two supports. If I put a weight here, exactly in the middle, again, any weights I put here will be equally shared by the two supports. If this represents a person is standing on the beam, and this person starts moving on the beam like this. Here, if we do calculation, we are going to learn how we do the calculation. We do the calculation of what we call the principle of moments, which we call the turning of the moment about any support clockwise equal the moments anti-clockwise. For example, if now I have this weight here, I take moments about this pivot, then what are the weights which will cause clockwise moment? The weight, let us say this is a person standing on the beam, the weight of this person making clockwise moment, the weight of the beam making clockwise moment, and the reaction at this supports making an anti-clockwise moment. But the moments, the sum of the moments of this weight plus the weight of the beam clockwise is the same as the moment of the reaction at that support. The reaction is up, therefore the moment is anti-clockwise, and these moments are clockwise. We will find that when this weight of the person is nearer to this support, the reaction here is larger than the reaction here. If this person moves on the beam like this, as he gets closer to this support, the reaction here will increase and this reaction will decrease. As the weight moves and comes in the middle, the two reactions are equal. As he moves to the other support, like this, then this reaction gets larger and that gets smaller, and so on like this. There's one very important thing you must remember, that if this is really an actual, right, this model, a real problem, and this person comes and try to move on this, what say the free side, and he tried to move, and he tries to move, there could be reach a point when what will happen, that the beam will be toppling over. Let us see. Right now you can see what has happened. The beam is toppling over. Why? Because this reaction reached zero. Now at this moment here, right, you can see now we are almost, you see, this reaction is not carrying anything. I can move it out, in and out, is not carrying anything. If the weight moves a little more, then toppling will happen. What do you mean toppling? That one reaction becomes zero. If the beam topples about this support, then the reaction about this support will be zero. Again, if the beam topples about this support, then this reaction is zero. And then if I want to know what is the furthest distance before toppling will happen, what I do is this. I take moments about this point. I have the weight of the beam. I multiply times its distance. This is a clockwise moment. Equal to the weight, which is a movable weight or the weight of the person, times distance x. Equating the clockwise moment, which is a value known, with the anti-clockwise moment, which is a weight known, but the distance unknown, and can know what is the furthest distance the weight can move before toppling happens. The same thing can happen on the other side, right? The same thing can happen on this side. The beam moves, I move the weight there, I move the weight there, I move the weight there, until at one point toppling will happen. You see? Now toppling will happen. Toppling will turn. Toppling means the beam will turn. The beam will turn about this pivot. Yeah, but the reaction at this pivot is zero. When the beam topples about this pivot, this reaction is zero. When the beam topples about this pivot, then this reaction is zero. Again, how do I find the further distance? I say the weight, for clockwise, and the known weight, the unknown distance, equal to the known weight of the beam times its known distance. From this I can calculate what is the furthest distance, right? The furthest distance the weight can be placed before toppling can happen. This is exactly represent all types of problems we are going to have. All types of problem will be like this. That could be the weight of the beam is here, the person standing here, standing there, is standing anywhere, and he asks you to calculate the reaction at the two supports. How do we do it? Say in this case, I want to know the reaction of the two supports. I take moments, say, about this support or this support. I take moment about this support. I say this weight of the beam in the middle times its distance clockwise. This weight vertical down times its perpendicular distance. This is clockwise. This is 2 moments clockwise, equal the unknown reaction times this known distance. Therefore, we have 2 known clockwise moments equal to unknown anti-clockwise moments. I mean, it is equal to it. What is unknown? The value of the reaction. So the action times the distance known, we can get the value of this reaction. Once I get the reaction here, I can get the reaction here easily. Why? Because also the forces are balanced. What means the forces are balanced? The sum of the forces up equal the sum of the forces down. So the weight of the beam plus the weight of the person down equal the sum of these two reactions. I got this reaction by calculation. Therefore, I can get this value of this reaction by subtracting the total weight minus this reaction, I get this reaction. This is really the type of problems of moments which we are going to have in problems. All problems like this. Or he could ask, the question is, where do you place the weight before the beam will balance? Let us have, say, now real problems in the board sheet here. Now, look at the board and we take the example, the first example in the book. The first example in the book, it says the following. It is example 7. Right. Example 7, we are given a beam like this. Beam. Now, this is a beam given. It is supported here by one pivot and supported here by another pivot like this. This is a beam supported by these two pivots. It says here that the distance there is 2 meters and this distance is 1 meter. And it says that the beam is uniform. The beam is uniform, its weight in the middle, so the middle is 1.5 meter. This is the weight of the beam. Right. Now the weight of the beam is 20 Newton. 20 Newton. This is A and this is B and this is D. This is C, sorry. And this is C. Right. It says calculate the magnitude of the reactions at each support. We want to find the reaction at each support. So what we are going to do? We are going to say moments about A. This terminology, moments about A. The 20 Newton makes a clockwise moment. The 20 Newton makes clockwise moment. 20 times this distance, 1.5. Clockwise moment. It's the only clockwise moment. Equal. The reaction at C, there's a reaction at C here. Anti-clockwise moment times 2. The perpendicular distance is 2 meters. We get the value of RC. 30 over 2 is 15. We know that RA plus RC equal 20. From this we get the value of RA equal 5 Newton. And this is the problem. The problem is moments. We took moments about A, 20 times that distance, 1.5. Why? Because the beam is uniform, then the distance is half the 3 meters. Even that distance is 1.5 meters. This is a clockwise moments with the clock, and because the weight is vertical, the perpendicular distance is horizontal. Then the reaction there, the reaction at C, I don't know it, but to multiply it times its known distance, which is 2, from which we got the value of RC. I got RC, and I know that RA plus RC equal 20, so we can get the value of RA equal 5 Newton. This is the first example. We go then to the second example. Right. The second example is now the second example, it says the following. It says an uniform beam AB supported in two supports. This is a uniform beam. It is supported in two supports, one support here and one support there. The beam is AB, and the two support, this is 1 meter and 1 meter. And the whole beam is 5 meters. Therefore, this distance is 3 meters. The center of mass in the middle. This means that distance is 1.5 meter, and this is 1.5 meter. Right. When a man of mass 80 kilogram is stand on the beam at point E, a man is stand at point, this is a man, is stand at point here, this point is E. When a man is stand at point E, the magnitude of the reaction at point D was twice the magnitude of the reaction at point C. The reaction at point like D, because these points C and D, this reaction was twice that reaction. It says here that this reaction is twice this reaction. So if this reaction, I call it R, then this reaction is 2R. The man of weight, the beam has a weight 40, mass 40 kilogram, its weight 40 G. And the man is 80 kilogram, its weight 80 G. It is required to find the distance AE. First, here in this problem, there is one distance missing. The question is to find the distance AE. When one distance is missing, then we cannot perform moments. Then we do, because we have two things we do. We are equalizing moments and we are equalizing forces. When one distance is missing, we do the equalizing of forces first, which means we are going to say R plus 2R equal 40G plus 80G. Means 3R equal 120G. يبقى R equal 40G. يبقى the reaction at C, RC, is 40G and RD is 80G. Now we take moments about point C. We always take moments about the left hand pivot. We take moments about the left hand pivot. But the moment about C. Now, the clockwise moments, 40G clockwise, ATG clockwise, and the reaction at D anti-clockwise. Again, the 40G makes clockwise moment. The ATG makes clockwise moment. And the 2R makes anti-clockwise moment. About 40G times its distance 1.5 plus ATG, its distance is missing. What is the distance from C to E? I call it CE. It is the distance CE. This is a clockwise moment, equal the anti-clockwise moment, which is the reaction at D, which is ATG, times the distance from C to D, which is 3. Now, 40, first we can say all the G's cancel. 40 times 1.5, 60, plus 80 distance CE equal 240. By 80 distance CE equal 240 minus 60. 180. The distance CE equal 180 divided by 80. 180 divided by 80, right. 2 is 90, 2 is 45, it is 2.25. It will be 2.25 meters. But he requires the distance AE, so we have to add 1 meter. But the distance AE is 2.25 plus 1, so the answer is 3.25 meters. But how far is the person will stand at a distance 3.25 meters? Now, we go to the next example. The next example, I can ask here one question on this example to make it extra question than we mentioned in the book. Can this man moves further? And the question is, how far this man can move beyond point D before the beam toppling? I am adding one extra question here than the example in the book. What is that question? How far this man can move beyond point D before toppling will happen? Now, let us look at this problem. Now, the problem is this man now will come here. The man ATG will come here. The man will come on this side. The man will come and stand here. This is the man. And we say a new point, we call it F. The man stands now at point F. The question is, what is the third largest distance, AF, before the beam will topple? When the beam will topple, the beam will topple about D. Again, the man is standing there. The man will make the beam turn. The man will make the beam turn about D. But the beam topples about D. But therefore the reaction at C will be 0. There will be no reaction at C. Whenever beam topple about D, but the other support has no reaction. And straight away we take moments about the point of toppling. We take moments about point D. We take moments about the point of toppling. Then we say now, I said the man is stand at a new point called F. We are going to take moments about D. The weight will make clockwise moment, and the weight of the person, and the weight of the beam will make anti-clockwise one. How do I know it? By I'm standing here, the D point D there, and the weight is there. It will turn the beam clockwise. But therefore 80 G times the distance DF, which we don't know it, equal 40 G times the distance from here to there, which is 1.5. From this we calculate the distance DF. It will be 0.75. Therefore, what is the largest AF, which means the largest distance from A? It will be 1.5, 1.53, 4.75 meter. This man means can stand safely at any point from C. He can stand at anywhere from C going to D, but he cannot go further than D by 0.75, 4.75 meter. That the maximum distance the man can stand is 4.75 meter. This is, I added a part to the question in the book to make it more, say, and enriching our knowledge of moments and the type of questions we can have. Now we go then to the next example in the book. The next example in the book, it say this, right? Questions say this. A uniform rod AB of length 4 meter. The beam, again, a uniform beam there. It has 2 supports. The distance now is 0.5 meter and 0.5 meter. The beam length is 4 meter, so this will be 3 meters. Okay, it is a uniform beam, its weight in the middle, so that distance 1.5 and 1.5, and the weight of it in the middle. The beam has a mass 12 kilogram, its weight is 12 G. It say a particle of mass M is placed on the rod at point D. The supports are, right, anyway, C and D. He said that the beam is AB. A particle of mass M, okay, right, a particle of mass M placed on the rod at point B. There's a mistake in the typing of the book. The particle is at point B. The particle is placed at point B, not D as written in the book. This particle mg, right? On the rod on the point of turning about D, mean the beam is now turning about to turn about D. He said here's the question. If the beam about to turn like topple exactly, turn about the beam, turn about D, you have a reaction at C equals 0. And straight away you take moments about the point of toppling. We take moments about the point of toppling. So we say M about D. mg times 0.5 clockwise moment. Why? This is a support and this is a weight turning clockwise. But here this is a support and that is the weight turning anti-clockwise, equal 12g times 1.5. The g cancel with the g, so we have 0.5g, 0.5m equal 18, يبقى m equal 36 kilogram. This is the weight of the particle which will cause toppling. Now, we can have additional type of problems. In this case, he would say that the beam is non-uniform. If the beam is non-uniform, then the center of mass is not in the middle. The question will be that he asks us to find where is the center of mass of the beam. Where is it? Right. Now, let us take a problem about, right. Now, example which we have, right, a non-uniform beam. Now, the first example, it is an example where the beam is non-uniform, but we are given where is the center of mass. But this is one type of problem. But another type of problem, it will be given that the beam non-uniform, and it is requested that we find where is the center of mass. We take the first problem, example 10. Example 10, it is like a seesaw. A seesaw where two people sits on the side of the seesaw. A seesaw, right, now of blank AB, of mass 25, the blank AB, right, of mass, right, 25 kilogram, length 4 meter. The blank is pivoted at M, the midpoint. There is a pivot at the midpoint M. Now the blank AB, the center of mass of the blank is at point C. The center of mass is here, and that distance is 1.8 meter. Fine. There are two persons sits on the beam. Right, the person I'm seeing has a mass 25 and sits at A. One person and has a mass 25 and sits at A. Here 25G. Okay, where Sam can sit on the blank, Sam has a mass 35. What you say, Sam, we don't know where is Sam sit down. Sam has a weight 35, right? And we want to know where he would be sitting, right? This is the point where the center of mass is called C. Let us call where the person sits point D. The question that we want to know, where this other person sits down. Now, the blank weight is 12, with blank AB of mass 25. The blank is also 25 G. Now we take moments about M. We always take moments about the pivot. This weight will produce a clockwise moment. Therefore, 35 G times the distance MD equal. This will make an anti-clockwise moment. 25 G times this small distance, 0.2 meter, plus the other weight, 25 G times the distance from here to there. The beam length was 4 meter, the distance from here to there is 2. Therefore 35, right, MD, all the G's was cancelled, equal 25 times 0.2 is 5 plus 50. The distance MD equal 55 over 35, which is 11 over 7. Right, this is the distance MD. Now, if we ask to find the distance from A, then we add, right, this distance is 1 and 4 over 7. If you want to get the distance from A to D, you add 2 meters. You get 2 meters plus 1 and 4 over 7. Therefore, the distance is 3 and 4 over 7 meters. This is where the other person should sit down. We go then to the next example in the book, is example 11. Now, example 11 is, right, it says a rod AB 3 meter long and has a weight 20. A rod, okay, 3 meter long now and has a weight 20 Newton. It is in a horizontal position resting on supports, right, C and D, the rod AB, and we have 2 supports C and D. We have a support C here and a support D there. This distance is given 1 meter and that given 0.5 meter. And the whole rod is 3 meters, but that distance in the middle is 1.5 meter. Now, the magnitude of the reaction at C is 3 times. The beam has a weight 20 Newton, we don't know where. But he said the reaction at C is 3 times the reaction at D. It says here that the reaction at C is 3 times the reaction at D. If the reaction at D is R, the reaction at C is 3R. The weight of the beam is 20 but we don't know where. We don't know where is the weight of the beam. Now, as I mentioned earlier, when there is one distance we don't know, say with a beam, the person will stand at point E. When there is one distance we don't know, I said we do the balance of forces first. Yani we equate forces first. Therefore we say 3R plus R equal 20, 4R equal 20, يبقى R equal 5. Now we are going to take moments. Now I will solve this problem twice. I'll show you the reason. Now, it is required to find how far is the center of mass of the beam here, 20 Newton, yani point E from point A. There are two methods I'm going to do. The first method I'm going to do is we're going to take moments about C. Take a moment about C, the 20 Newton, طبعا, why I forgot maybe to explain, when we take moments about C, we don't include the force. Why? Because its distance is 0. Maybe I forgot to mention this earlier, that when we take moments about C, we don't include the force at C. Why? Because it has no distance. If it has no distance, because moment is force times distance. If the distance points come nearer, nearer, if the point is on the line, on the force, then it has 0 moment. Therefore, when we take moments about C, I don't include the force at C. Moment about C, if we include, say, 20 Newton times the distance CE. This is the clockwise moment, equal the anti-clockwise moment is the reaction R, which is 5, times the distance from C to D, 1.5. Therefore, the distance CE equal 7.5 over 20. Right. This is 0.375. But how far from A? The distance AE is 1.375 meters. The other way, you take moments about A. You use more work, but you get the distance of AE straight away. Now, when you take moments about A, I have one force clockwise and two forces anti-clockwise. Again, one force clockwise and two forces anti-clockwise. We have 20 times the distance AE equal the reaction at C, which is 3R, 15, times the distance 1 meter, plus the reaction at D, which is 5, times the distance from A to D. From A to D is 1 meter plus 1.5 meter, 2.5 meter. But 20 AE equal 15 plus 12.5, which is going to be 27.5. So what is the distance AE? 27.5 over 20, 1.375 meter. This is the right end of the all examples in the chapter. Now I just say some few things. I say again, when we take moments again about point like point C, I said when we take moments, all the previous problems, when we took moments about one pivot, I don't include the force at that pivot. Why? Because its distance is 0. Then any force, I look at it and I found where the force compared to the pivot. The force is here to the right, but therefore it will turn the beam clockwise. When the force is there and acting up, it will turn the beam anti-clockwise. Therefore we are balancing forces and we are balancing moments. Sometimes we do moments first, then forces. And sometimes we do forces first, then moments. This is the idea of the topic. Now you are able to solve any problem. Don't forget, whenever it says that the beam is going to topple, the beam will topple about point at two supports, and the beam will topple about whatever point he say, then you straight away take moments about that point, and the other support reaction will be 0. It say topples about D, but we are going to take moments about D, and the reaction at C will be 0. This is the idea of all problems, and then you can solve any problem in the exercise. Best of luck.